I am Dong Yang from Southern University of Science and Technology in Shenzhen, China. I'm very glad to host Dr. Huahua Xiao's talk today. Dr. Huahua Xiao is currently a professor in the State Key Laboratory of Fire Science at the University of Science and Technology of China. He received his PhD from the University of Science and Technology of China in 2013. Before coming back to the same university in 2018 as a professor, he worked as a postdoc and a research assistant professor at the University of Maryland between 2014 and 2018. And his research has focused on premixed flame dynamics, deflagration to detonation transition, the exciting blue wires, numerical algorithm and model development, and hydrogen safety. Today, he's going to give us a talk on flame pressure wave interactions and the flame instabilities in vessels. So before handing the floor to Dr. Huahua Xiao, I would like to remind the audience that you are very welcome to raise questions during the talk. So please use the chat function at the bottom of the screen, type into your questions there, and I will ask on behalf of you at the end of the talk. So now, Dr. Huahua Xiao, the floor is yours. Please start when you are ready.
Dr. Yang, thank you for the introduction. Hello, everyone. Thank you for coming, and thank the committee for organizing this combustion webinar. Today, I'm going to talk about the flame pressure wave interactions and the flame instabilities in vessels. I will also take this opportunity to present some of our studies on this topic. First, I would like to acknowledge my colleagues, such as Dr. Oran and Hoim at the University of Maryland, and Dr. Jinhua Sang and Dr. Xiao Sen, who contributed to the experiment I will show below. When I worked at the University of Science and Technology of China, before I went to the United States. My research has been supported by several sponsors, such as NSFC, Office of Naval Research, and Chinese Academy of Sciences. Premixed flame dynamics in vessels or tubes is very important for the explosion safety and the performance of combustion engines. For example, a hydrogen explosion occurred in Norway in 1997 in a pipeline. As you can see in the top right figure, the pipeline was broken into pieces, and the buildings surrounding were damaged. However, it's not clear if this was caused by pressure waves or detonation. Explosions also occurred in other scenarios, such as Li-ion battery module or containers, as flammable gases are released into the chamber due to thermal runaway wave, such as the explosion in Beijing last year. Internal combustion engines often use closed chamber or vessels for combustion. In particular, the wave rotor or wave disk engines uses constant volume combustion vessels. In general, an initially laminar flame propagating in a vessel can undergo a series of changes in its shape and structures as it propagates, such as spherical, curved, finger-shaped, concave, or cellular flame front. The regimes of the flame can undergo complex changes as well. It can change from laminar to turbulent, from subsonic to supersonic, and even deflagration to detonation. The reason is that the flame dynamics can be influenced by various phenomena such as fluid dynamic instabilities, combustion instabilities, vertical flow, boundary layer effect, and the pressure waves. For example, as shown on the top right images from our experiment, the flame can be unstable due to the Landau instability or the thermodiffusive instabilities. Among these phenomena, the pressure waves have a direct and important effect on flame instabilities. It can cause relatively instability as acoustic waves, as shown on the right figure. When a curved flame front is exposed to a sufficiently strong pressure wave, significant flame wrinkling can be caused by the pressure wave. As shock waves, they can cause Richmond-Mascoff instabilities. This effect can cause very high peaks in overpressure that can cause damages to surroundings or the chamber itself. There are actually several challenges to examine or explore the flame and the pressure interactions, because it's very hard to detect or check the pressure waves in experiments. And the differences in time and length scale poses difficulties for numerical simulations. Also, it's difficult to separate the pressure wave effect from the effect of other factors, like the vortex and thermodiffusive instabilities or Landau instabilities. In the past, idealized model with artificially imposed pressure waves were often used to provide the fundamental knowledge of flame pressure wave interaction, but only to a limited extent. There are still issues in real scenarios, such as how to understand the dynamics of the pressure and the flame interactions, and how do we quantify the pressure wave effect if we have them. So to model typical scenarios, we started from experiments that used a closed vessel filled with hydrogen-air mixtures. In the experiment, the flame is ignited near the left end wall of the vessel, and it propagates toward the opposite end. We use high-speed Schirring photography to record the flame evolution, and we use pressure transducer to measure the pressure dynamics. In the experiment, we observed a concave flame phenomena, what is usually called tulip flame. So what is tulip flame? As shown by this video and this figure, we can see that a tulip flame is a premixed flame with its cusp pointing toward the burned region. So there is a long history of studies of tulip flame formation since this phenomenon was first photographically reported by Alice in 1928. However, there is a strong controversy about what causes its formation. This table lists 5 popular explanations for this phenomenon. Yes means the authors proposed or support the explanation in in the row, no means the authors disagree with this mechanism. For example, Rothman and Oppenheim and Matlin et al. thought that vortex motion in the boundary region is the cause of tulip flame formation. However, Dan Rankin and Ponid et al. thought that it's not the case. And this guy, Ponid, it seems he doesn't like anything. Now, the situation is further complicated by the discovery of distorted tulip flame in our experiment. This video shows the result measured in our experiment. So what is a distorted tulip flame? It's actually a flame front with additional cusps superimposed on the primary tulip lips, as you can see here. As a well-pronounced distorted tulip flame is formed, the flame front looks like a triple tulip flame. This flame phenomenon is actually very robust. We conducted parametric studies using different compositions. It's conform in most of the cases. Okay. In addition, the experiments also showed that the oscillation of flame propagation and pressure growth rate are very significant, as shown by this figure. You can see that the flame propagation speed oscillate in a very similar phase and the frequency with the pressure growth rate. This shows a hint of interactions between the flame and the pressure waves. However, in the experiment, we could not know how the pressure waves are generated and how they propagate and they interact with the flame front. Although interesting experimental results were observed, but the dynamics of the flame pressure wave interactions are not well understood. There are still many questions unanswered, such as how do the pressure wave form, propagate, and interact with the flame front in the vessel to cause flame instabilities? What is the role of pressure waves in the initiation and the growth of the flame instabilities, namely the distorted tulip flame? Can we quantify the effect of pressure waves? So in order to answer some of the questions, we conducted numerical simulations. We developed a numerical simulation model and reproduced the experimental observations. This video, this is a video from our numerical simulations. This case is a vessel with a size 4 centimeters by 28 centimeters. This is a base case of a series of computations in our study. Now let me play it. Oh, sorry. So as you can see, after ignition, a spherical flame front develops, and pressure waves are generated by the ignition, but they are weak. Then the flame front is elongated in the longitudinal direction. And after that, the flame touches the tube sidewalls, more pressure waves are generated. Then the flame front is flattened out and a tulip flame is formed. After a well-pronounced tulip flame forms, distorted tulip flames start to form. As the first distorted tulip flames disappears, a second one start to form. Actually, this process repeat until the end of the combustion, and a series of distorted tulip flames are formed one after another in the process. From the numerical simulations, we can see the pressure wave interactions with the flame front. Okay, our numerical simulations were validated against our experiment. This figure compares the experimental observation with the numerical simulations. Overall, the experimental observations are well reproduced by the numerical simulations. For example, the tulip flame, as shown here, is in very good agreement with the numerical simulation. In particular, the distorted tulip flame is well reproduced by the simulation. In addition, the second distorted tulip flame observed in the experiment is also well produced. More verification and validation of our numerical simulations can be found in our 2005 CNF paper. Okay, now let me show you how we obtained the above numerical result. In our numerical simulations, we solved the two-dimensional fully compressible Navier-Stokes equations. The fully compressible model includes all the acoustic waves. If they are important, we will see it. Okay, the combustion model of stoichiometric hydrogen-air mixture is modeled using a simplified chemical diffusion model. In this model, the reaction rate is calculated using Arrhenius equation like this. The transport properties are calculated as a function of temperature. This combustion model was originally developed by Elaine Oran and her colleagues. It can reproduce the major properties of flame detonation and the transition between them for premixed combustion. We solve the governing equations using a Gottlieb type method, which is fifth order in space and the third order in time. Adaptive mesh refinement helps us resolve key features of the flow, such as the flame boundary layer and the pressure waves. This approach has been verified against many problems before we do the actual calculations, such as a variety of structural problems, premixed flames, detonations, and DDT. The computational domain is a series of closed vessels with no slip adiabatic boundary conditions at all the walls. Two sets of vessels are considered in the numerical simulations. The first set is the vessels with the same aspect ratio but different sizes. The second set considers tubes with the same diameter, 4 centimeters, but different aspect ratios, 3.57 and 14. This two set of vessels can help us to quantify the effect of pressure waves, as will be shown later. In this slide, the left-hand side figure shows the flame surface area and the flame propagation speed as a function of time. The right-hand side figure shows the pressure and its growth rate as a function of time. The results show that the pressure wave causes significant oscillations to the flame front and the pressure growth rate, just as we see in the experiment. Every time the pressure wave hit the flame front undergoes a sudden deceleration. After the pressure wave passed through the flame front, the flame experience at an acceleration actually. Then a distorted tulip flame forms. The result here confirms the flame oscillations observed in the experiment. These oscillations are caused by pressure waves. So the question is, how are the primary pressure waves are generated? Our numerical simulation showed that the primary pressure waves are generated by the early contact of flame front with the side walls. And these waves are demonstrated to be expansion waves because the pressure decreases behind these waves. Let's see this video again. Here, the primary pressure waves are generated as the flame front touches the tube side walls. Okay. Additional pressure waves are generated in the evolution of tulip flame and distorted tulip flame themselves. This pressure and this process repeats, more pressure waves are produced. These pressure waves can coalesce with the primary pressure waves and produce stronger and stronger pressure waves. So now we have known how the pressure waves are generated. So let's take a look at the formation mechanism of the tulip flame and the distorted tulip flame, namely the instability phenomena. For the tulip flame, here we show the streamlines and the pressure fields. The results show that before the tulip flame is actually initiated before the primary pressure waves hit the flame front. So this means the formation of the tulip flame does need pressure. The results actually show that the tulip flame is initiated by the large-scale vortex motion just behind the flame front in the region. Therefore, our report the vortex motion mechanism, and we say no to the pressure wave effect. So what about the distorted tulip flame? Here we show the streamlines and pressure fields for the time instant when the distorted tulip flame forms. The result indicates that tulip flame forms through, as shown here. The distorted tulip flame actually is formed as the primary pressure wave pass through the flame front. So this implies the pressure, the direct if the flame. But we still don't know the play in the formation because this is just a flow field. So before we answer these questions, we first examine the amplitude or strength of the pressure wave to see if the pressure waves are strong enough to cause the instabilities. So the left-hand side figure shows the pressure left-hand side figure shows the pressure profiles as two pressure profiles as 1,000 Pascal. The right-hand side figure shows the pressure distributions as the longitudinal pressure distributions at the first distorted tulip flame forms. The pressure differences across the flame front is about 18,000 Pascal. According to Xiao et al., a pressure wave of amplitude greater than 1,000 Pascal can lead to strong flame wrinkling through residual instabilities. In our case, the pressure difference for distorted tulip flame can be as high as 18,000 Pascal. So the pressure wave is strong enough to wrinkle the flame through residual instability. Based on theory, when a curved flame front is exposed to a pressure wave, there is a strong misalignment between the density gradient and the pressure gradient. So the flame front can be disturbed by the relative instability due to baroclinic effect. For the tulip flame, the baroclinic torque can distort the flame front in this manner, according to the right-hand rule. Yeah, this is just the distorted tulip flame. Similarly, it looks like distorted tulip flame. But so what about our numerical simulations? So our numerical simulation also shows similar observation. Therefore, the numerical results support the relative instability. But here it's only qualitatively support the relative instability. So the question is that can we quantify the effect of the relative instability? So before we answer this question, we examine the result for different vessels with different aspect ratios. Here we show the result for the vessels with a fixed aspect ratio of 7. The results show that the flame develops in a very similar patterns for all the 4 tubes. But for a longer vessel with an aspect ratio of 14, the flame develops more drastic instabilities, and actually very strong pressure waves are produced, even shock waves forms. However, by contrast, for the shorter vessel with an aspect ratio of 3.5, only tulip flame forms. The distorted tulip flame does not form in this case. In addition, the analysis showed that the distorted tulip flame forms at the same non-dimensional times. The time is normalized by a characteristic acoustic time. In this slide, the left-hand side figure shows the flame normalized flame front propagation speed as a function of time, and the right-hand side figure shows the normalized flame speed as a function of time for the set of tubes with different aspect ratios. The left figure shows the result for the vessels at the same aspect ratio. So the results show that for all the tubes with tulip flame formation, the flame speed oscillate in a similar pattern, in a very close pattern. That is, the flame oscillation phase and the frequencies are very similar for all the cases, for the fixed aspect ratio case. Even for the cases with varied aspect ratio, the oscillation are also very similar for the distorted tulip flame. Here, the formation time of distorted tulip flame is denoted as tom. For example, the first distorted tulip flame formation time is marked as tom DTF1. Yeah. So the conclusion here I would like to remark is that the pressure wave controls the formation and the evolution of the distorted tulip flames. Similar observations are also shown by the pressure wave oscillations, as shown here by these two figures. So in order to quantify the pressure wave effect on the distorted tulip flame formation, we performed a theoretical analysis based on a linear theory. In this analysis, the growth rate of relativity instability is calculated using this equation. Here, K is the wave number. We assume the distorted tulip flame has two wavelengths, so the wave number can be calculated using this formula. G means the flow acceleration. Here we define a fluid number to determine if the flow acceleration is sufficiently high to cause the relativity instability. In addition, we defined a time scale ratio to see if the relativity instability has enough time to develop. Here, SU means laminar burning velocity. D means tube diameter. The time scale ratio is defined as the ratio of growth rate to the reciprocal of half oscillation period of pressure wave. Because the pressure wave inside the vessel is actually a half wave mode. Now let's take a look at our result. This table lists the result of the theoretical analysis. You can see for all the cases with fixed aspect ratio 7 or different aspect ratios, the fluid number is on the order of 10 to minus 3. That means the flow acceleration is strong enough to allow the relativity instability to develop. Okay, let's take a look at the time scale ratio. So for the time scale ratio, things are different. For the set of vessels with a fixed aspect ratio of 7, the time scale ratio is about 2.5 or 2.6. This means for these cases, the relativity instability has enough time to develop. For the longer tube, the time scale ratio is even much larger, 5.9. So this means the relativity instability has even more time to distort the flame front to a greater extent. By contrast, for the short tube, namely the vessel with an aspect ratio of 3.5, the time scale ratio is 0.9, less than 1. So this means the time scale ratio does not allow the relative instability to develop. This is why we did not see distorted tulip flame for the short tube, namely the 4x14 tube. So in conclusion, our numerical simulation and the subsequent theoretical analysis quantitatively demonstrates that the formation of the distorted tulip flame is caused by relative instability driven by pressure waves. The above result shows the details of the dynamics of flame and pressure wave interactions. And the result also shows how we understand the mechanisms of the instability phenomena, namely the distorted tulip flame, and how we quantify the effect of the pressure waves. Next, I would like to take some time to talk about the influences of wall boundary condition on the flame dynamics and the pressure wave flame interactions. We examined the effect of aspect ratio and the diameter of vessel on the flame dynamics. But what is the effect of wall boundary conditions on the flame dynamics? Actually, there is an argument on the role of wall boundary conditions for tulip flame. For example, Mara et al. Thought that wall friction is the determining cause for the formation of tulip flame. However, Gonzalez and our prior work showed that wall friction is not important for the tulip flame formation. And also Lee and Kim thought that the heat losses at walls have a significant effect on the flame propagation speed and the structures. Although there are some studies about the wall boundary condition effect on the flame dynamics, but a complete understanding for the wall boundary condition effect has not been obtained, especially for the flame pressure wave interactions and the distorted tulip flame formation. So in our work, we consider 3 different types of wall boundary condition. The first condition is adiabatic no-slip boundary condition. The second condition is the adiabatic free-slip condition. The final one is the isothermal boundary condition. This is actually a no-slip boundary condition. So now let's take a look at our result. Let's first recall the adiabatic no-slip case, as I just showed a moment ago. In this case, the flame develops as a classic tulip flame and a series of distorted tulip flames, and finally a significantly wrinkled flame. For the adiabatic free-slip case, things becomes different because the pressure waves are amplified to form shock waves, as shown on the left-hand side of figures. Shock waves forms in the later stages, and the shock waves interact with the flame front to cause corrugated flame. As shown here, the pressure waves travels back and forth inside the vessel and cause corrugated flame front. For the isothermal case, even stronger shock waves formed in the later stages here. And the flame are distorted to form a highly corrugated flame front as shown on the left-hand side images, also shown in the video. So what is the reason of this phenomenon? So before we answer this question, we take a look at the details of the pressure waves. For the adiabatic no-slip case, only acoustic waves are produced in the entire process. For the adiabatic free slip case, shock waves at Mach number about 1.06 are produced in the later stages. The shock wave is stronger for the isothermal case. It can have a Mach number of 1.13. So this implies the word boundary condition has a significant effect on the pressure wave generation and amplification. Because first we, even for the adiabatic free slip or the isothermal case, we initially don't have shock wave. We only have acoustic waves at the beginning, but as the flame propagates down the tube, these acoustic waves are amplified to produce the shock waves. These two figures show the flame tip position and the flame propagation speed as a function of time. The results show that the adiabatic no-slip case has a larger flame propagation speed as shown by the green curve. However, the adiabatic free slip case and the isothermal case shows stronger flame oscillations in the later stages, especially for the isothermal case. It has the strongest amplitude of oscillations, as indicated by the red curve. Similar trends are observed for the pressure oscillation. I'm not going to go into the details here. Of course, since we have we have shock waves, so the flame shock interactions can lead the distorted tulip flame to evolve into a highly corrugated flame front by triggering the Ridgmeier-Meshkov instability, as shown here. For the adiabatic free slip case, as after the shock wave passed through a curved flame front, we can see the bubble and the spike structures are formed for the flame front, and the flame cusp are topped off with mushrooms in the flow. These features are more pronounced for the isothermal case because the shock waves are stronger. So what is the reason? Let's first take a look at the initial strength of the pressure wave. As we talked few minutes ago, the pressure wave, the primary pressure wave is actually produced by the contact of the lateral flame front with the side walls. So this caused the sudden loss of flame surface area. Then the loss of expansion source caused the expansion waves. So the loss of the flame surface area determines the initial strength of the expansion wave. So now let's compare the lost flame surface in these three cases. The results show that the adiabatic free sleep case had the largest flame surface area lost, and the isothermal case had a smaller one. The adiabatic no sleep case had the smallest flame surface area lost. So this the flame surface area lost can determine the variation of the heat release or heat loss, and the heat release, the variation of heat release determines the amplitude of pressure oscillation or pressure waves. So the result is that the adiabatic free sleep case had the highest variation of heat release or heat loss rate. The isothermal one has the second has a moderate variation of heat release, while the adiabatic no sleep case had the smallest value. So this is very easy to understand. So, but why we observe strongest pressure wave in the isothermal case instead of the adiabatic free sleep case? The reason is due to the heat conduction through the side walls. Now let's take a look at the heat losses in the isothermal case. So we consider the heat loss. We just consider the heat losses at the pressure wave generation stage at the beginning. So we calculated the heat losses using these equations. Using this equation here, delta Q is calculated using this equation. PQ is the Peclet number, it's 1.4, and the delta L is the laminar flame thickness. Actually, delta Q is the thermal thickness here. So Ka is the average thermal conductivity between the start point and the end point of the contact area. So we found that the heat losses is about 66 kilowatt. So if we summarize the heat, the variation in heat release rate and the heat losses, we can get 287 kilowatt. So the isothermal case had the largest variation in heat release or heat losses. That's why the pressure waves are amplified in this case to form the strongest shock wave. To summarize, this talk actually gives 5 major conclusions. The first is the pressure waves has a strong effect on the stability of flames propagating in vessels. The acoustic properties control the formation and evolution of the instability phenomena, namely the distorted tulip flame. The relative instability driven by pressure waves is the primary cause for creating the distorted tulip flames. Wall boundary conditions strongly influences the strength of pressure waves, and thus the pressure flame interaction. The way how the lateral flame front touch the side walls and the heat losses through the tube side walls are important in the generation and amplification of the pressure waves. Okay, that's all for my presentation. Thank you. Please feel free to ask any questions.
Thank you very much, Dr. Huahua Xiao. I hope you can hear me.
Yes, sir.
My internet
yes, I can hear you. Thank you.
Yeah, so I turned off my video. We do get, I think, one question now. This is from Jay Guo. The question is, so great presentation and review. Could you comment if two-dimensional simulations are sufficient for explaining these fundamentals? Are there significant three-dimensional effects?
Yes. Okay, good question. Actually, we think two-dimensional simulations can help explain the most part of the flame pressure wave interactions in our case. Because the flame phenomena observed in the experiment can be well produced by the two-dimensional simulations. This is one reason. Another reason is that the flame, the experiments were conducted in a vessel, actually with a square cross section. So the flame, the pressure waves in the two-dimensional simulations can behave in a similar way in three-dimensional case. Yeah, that's my answer. I'm not sure if I answered the questions sufficiently.
Yes, thank you so much for the answer.
Okay, thank you.
So, okay, we have two more questions. The second one is from Xiao Go. So thanks for the nice talk. In practice, pressure waves in different directions may be generated in vessels. Which pressure waves need to be considered?
Here. Okay, let's show the pressure wave generation and the propagation in the video. So as you can see here, the pressure wave can be generated in different directions, but after they travel back and forth inside the tube, they will be flattened out to form a primary pressure wave that propagate primarily in the longitudinal direction. So I think only the pressure waves propagating in the longitudinal directions are the determining pressure waves for the flame instability. Yeah, I think this is a good question. Yeah.
Okay. Yeah. So my understanding for this, if correctly, is I think when your pressure wave is generated, it's initially kind of going to everywhere in all the directions. Yeah. But when it propagates, right, as we are considering kind of a very narrow channel. So then when it propagates away, it becomes a plane wave.
Right, right. Yeah, if you have a square vessel, then things can be different, I think.
I see.
But for square vessels, the amplification of the pressure waves will be not so significant. The pressure waves can be amplified in the thin vessels.
Okay, let's continue. So there are more questions from Zheng Chen, Professor Zheng Chen. So the question is, thank you for your nice talk. Why does the flame acceleration becomes stronger at higher aspect ratios? What's the physical mechanism?
This is a good question. So here, because in the longitude, in the long tube, like in this case, the flames, the loss in the flame surface area as the lateral flame fronts touch the side walls is much larger than the other tubes. That's why the pressure amplitude is greater in this case, according to this equation, because the pressure amplitude is proportional to the variation in the heat release rate, and the heat release is proportional to the variation to the flame surface area. Yes, this is the answer to the question.
Okay, that's
I'm not
fantastic.
sure if okay.
So there are a bit more comments. So besides the RT and RM instability, there is hydrodynamic instability, like the Darius-Landau instability. Is the hydrodynamic instability important?
We don't think the Darius-Landau instability is important, because Darius-Landau instability is actually a slow mode instability. In our case, the time scale is not enough for the Darius-Landau instability to develop. The Darius-Landau instability usually can be seen in the explosions in open atmosphere, because in those cases, the flame propagate much slower, and the Darius-Landau instability can be significant. Yes.
So that's quite interesting. When I see this result, this reminds me a lot about the thermoacoustic instabilities, like in the gas turbine combustor.
Right.
But in this case,
right.
the primary pressure wave generated by the sudden change of the heat release rate, that's dramatic. So that's the different
right.
situation. You are in this kind of very confined vessels, I think.
Mm-hmm.
Yeah.
Right.
So next question is from Professor Yi Guangzhu. I think friction has a different mechanism in affecting the pressure. Friction changes the flame shape and convert kinetic energy of the flow into heat. Therefore, friction will weaken the compression effect and the pressure wave. Could you clarify this?
So friction can weaken the pressure wave, right? So do I understand it correctly?
Yeah, I think that's one part of the comment. It can also change the flame shape.
Yeah. Yes. It's a very good question. So in this talk, actually, I did not I did not go into that detail. Let's take a look at this figure. Here we can see that due to the friction of the side walls, we can see the flame shape actually changes. A flame shape. I mean, there is a slightly there is a slight bug here. You can see here that propagate a little bit faster than the major part of the lateral flame front, and they get closer to the side wall at an early time. So this can actually affect the flame surface area lost when the flame lateral front touches the side walls. Compared to the adiabatic free slip case, there is no wall friction. We can see that the flame front near the side wall does not change its shape actually. So when the flame lateral front touches the sidewalls, the lateral flame front is almost parallel to the sidewalls. This caused a larger reduction in the flame surface area when the flame touched the sidewalls. Then the free slip case, then the no slip case, as you can see here. So that's why the initial pressure wave in the adiabatic free slip case without wall friction is stronger than that in the no slip case. So this is the answer for the first question. The second question is that the wall friction can reduce the strength of the acoustic wave. I did not consider that question before. This is a very good question. It's maybe possible, but I don't think it's that important. It may not affect the result that much. The wall friction actually can disturb the flame front to a larger extent compared to the adiabatic free slip case, as you can see here, because in order to satisfy the continuity equation, the flame front has to be curved for the adiabatic no slip case with wall friction. Yeah, that's my thought. I'm not sure if I answered this question correctly or satisfactorily.
That's interesting. I think regarding the acoustic damping, I think apparently the major source is the monopole acoustic source generated by the big heat release disturbance. Let's see, when the flame length suddenly change, the flame surface length. Sorry. Regarding the damping, I have the feeling that the acoustic damping should be small in your case. I mean, the viscous damping on the wall. But I guess that at least depends on the let's say the Reynolds number of the flow near there. We do have another question. I think it's from the audience, Ahmed. So thanks for the nice presentation. Did you work on quantification of flame instabilities based on various pressure waves? I wonder that, are you able to quantify the effects of various pressure oscillations on flame instabilities? So this is the various pressure waves.
We did do the quantification for various here means acoustic waves, shock waves. So in the theoretical analysis of the relativity instability, we actually quantify the effect of acoustic waves. Here, for the shock waves, we also quantify the effect of the Richmond-Mashkov instability. Actually, because we calculated the Mach number of the shock waves. Yeah, here. Once we have the Mach number of the shock waves, then we can quantify the effect of the shock waves.
I would like to thank Dr. Huahua Xiao again, and that is the end of our webinar today. Thank you very much.
Okay, thank you, Dr. Yang. Thank you all.